The room hums like a held breath. In the glow of indicator lights, a digital computer waits, a patient clerk who never sleeps, a factory line with no hands, a stagehand that knows every cue by heart. Give it a set of instructions, and it will work for you with a devotion that borders on eerie. Those instructions, arranged as a sequence, are a program, and down in the wire and silicon, the only things that truly matter are small, stubborn acts. Add 2 numbers. Check if a value is 0. Copy this bit of memory over there. The primitives are tiny, the way stair steps are tiny, but 1,000,000 steps will still carry you up a mountain. That bottom dialect, the one the circuits conduct like a minimalist symphony, is machine language. Engineers decide which notes exist in that symphony. Fewer notes make cheaper instruments, so the base instruction set stays austere. This austerity creates a gap between what people want to say and what machines can hear. People want to say, model the climate, train a language model, settle a stock trade in less than a heartbeat. The machine replies, I can add, compare, and move bytes. Somewhere in that gap lives computer science, with its ladder of abstractions and its ceaseless effort to translate human intention into electronic action. There are 2 classic ways to cross the gap. 2 ferries that run back and forth on a dark river. One is translation. You take a program written in a language that is comfortable to the human mind, call it L1, and you replace each of its sentences with a string of L0 sentences, the terse speech of the machine. When you are done, the human words are discarded, and only the machine's new script remains. The other ferry is interpretation. You keep the L1 program as it is, then write an L0 program that reads each instruction in L1 and acts out its meaning immediately. Translation rewrites the book before it is read. Interpretation reads the book aloud in real time. Out of these ferries comes a powerful ghost, a virtual machine. Pretend there is a computer, call it M1, whose native language is L1. Pretend it is as real as brass and glass. You can write programs as though M1 existed, then either translate or interpret them on the very real M0, the hardware beneath your fingertips. If L1 is still not kind to the human tongue, invent L2. And if that still chafes, invent L3. Keep climbing, keep layering. Above the thrum of transistors, you can build floors of comfort, each one a language more humane than the one below. When you stand at the top and press a single key to sort 1,000,000 records, you are leaning on the work of every floor. Think of a modern machine as a tall building, a haunted hotel with floors that never end. On the basement level sits digital logic, the world of gates that speak in ones and zeros, of wires that carry 2 discrete voltages and pretend that physics is either this or that. A handful of gates create a 1-bit memory. A roomful make a register that can hold a small integer. A carefully arranged corridor becomes an arithmetic and logic unit. Above that basement is the microarchitecture, where collections of registers and the ALU take turns, shuttle data, and form a data path. Sometimes, a small built-in program, called microcode, choreographs each shuffle. Sometimes, that choreography is bolts and gears, hardwired, no script at all. On the next floor stands the instruction set architecture, the ISA, the version of the building that programmers see in manuals that say things like principles of operation or machine language reference. This is the level at which ADD and load and jump acquire their precise meanings, the level that pretends to be the whole machine even when, beneath the floorboards, an interpreter is pulling the strings. Above that is a hybrid level where the operating system lives. A stern concierge who adds new powers, such as processes, files, memory protection, and the strange spell called a system call. Some instructions in this hybrid level drop straight through to the ISA. Others are intercepted by the concierge and carried out with bureaucratic care. Higher still, the world becomes symbolic. Assembly language replaces raw numbers with mnemonics that humans can read witho+out going cross-eyed. Then come the high-level languages, a great flowering of dialects with names that have become folklore. C, C++, Java, Python, Perl, and many more. They are translated by compilers or interpreted by interpreters, or both, sometimes even at once. Each language defines a virtual machine, and each virtual machine can be built as software atop a real one. The hotel has no last floor. If a new level makes life easier, someone will lay down carpet and move in. The idea of building a tower of levels did not arrive fully formed. In the earliest days, there were only 2 floors, a raw split between electronics and instructions. In 1951, in Cambridge, Maurice Wilkes proposed a 3rd floor called microprogramming, a way to simplify fragile vacuum tube hardware by putting a small, specialized interpreter between the ISA and the logic. It was like inventing a resident librarian who knew how to fetch the right sequence of moves for every instruction. The result was reliability at a time when glass tubes glowed hot and failed often. The librarian learned the patterns once, then played them back forever. A few years later, another kind of librarian took her seat. Programmers had been operating machines by hand, loading compilers from card decks, feeding their own cards, waiting, and then feeding more cards. The ritual on an IBM 709 running the Fortran monitor system, called FMS, could swallow a night. The programmer Bret Easton Ellis might have called it glamorously tedious. John Backus at IBM had led the creation of Fortran to spare people from writing in raw numbers, but the machine still required a human attendant. Around 1960, the operating system arrived, a resident program that would read control cards like a priest reading psalms. A card that said *Fortran meant compile, a card that said *Data meant run. At Dartmouth College and at the Massachusetts Institute of Technology, the concept grew teeth. Dial-in terminals led to time sharing. A single machine became many rooms, each with a typist at a teletype hearing the clatter of its own private world. Once the microcoded librarian existed, designers discovered a dangerous pleasure. If a new instruction seemed useful, they could add it to the microcode. Why not include INC to add one, even if ADD already did the job? Why not add integer multiply and divide, floating point operations, procedure calls, character string operations, array indexing, relocation, interrupts, and fast process switching? The instruction sets swelled, like novels with too many minor characters. In time, a reaction formed. At IBM, John Cock championed a stripped-down approach that emphasized a small set of simple, fast instructions. The movement came to be known as reduced instruction set computing. Over on the West Coast, David Patterson at the University of California, Berkeley, and John Hennessy at Stanford University built the intellectual scaffolding. MIPS and Spark soon ran through the halls. In Cambridge, a small team at Acorn created the architecture that would become ARM, whose descendants now live by the billions inside phones and sensors and satellites. The pendulum never stopped. In the 1990s, mainstream desktop processors kept their baroque, complex instruction sets, but quietly translated those complex instructions into internal micro-operations that look suspiciously like reduced instructions. Translation at the gate of execution made the old ornate language run on a modern internal tongue. Meanwhile, Java arrived from Sun Microsystems under the guidance of James Gosling. It promised the ancient dream that a program could be written once and run anywhere, so long as the place had a virtual machine that spoke Java bytecode. Interpreters became just-in-time compilers. And then the just-in-time compilers became optimizing monsters that learned the habits of running programs and rearranged them on the fly. In web browsers, engines like V8 turned JavaScript into a racing machine. The ferries across the river multiplied and began to race one another, each trying to carry intent to action with fewer stalls and fewer regrets. Across the years, the operating system grew from a card reader clerk into an urban planner. It created the illusion of many programs running at once, enforced permissions, guarded memory, scheduled the CPU, and taught disks to pretend they were directories full of human-named files. The system call interface became a shrine, a narrow doorway through which ordinary programs could petition the kernel. Around that shrine, new rituals formed. At IBM in the 1960s, CP and CMS pioneered hardware virtualization, slicing a mainframe into many pretend machines and letting each one believe it owned the hardware. Decades later, the cloud made this sleight of hand the default reality. A single metal server might host hundreds of virtual guests. Containers made the trick lighter, sharing a kernel but wrapping each application in its own small room, quick to build, cheap to destroy. Psychology had a quiet vote in all of this. A human mind carries only so many items in working memory, often described as 7, give or take 2. Abstractions reduce the number of items that must be juggled at once. A function name replaces 100 lines of code. A high-level language replaces a sea of opcodes. An application programming interface is a promise that you can use a tool without knowing how it is forged. Every level is a cognitive contract that says, focus up here and we will keep the basement dry. The price of that contract is trust and the quiet dread that beneath, something might be leaking. There is another cost. Abstractions multiply, and with them the places where things can go wrong. A missing check at the operating system shrine can give a stranger the keys to your house. A wrong assumption in a hypervisor can expose neighbors in the cloud. A flawed JIT optimization can miscompile a loop on a Thursday and pass tests on Friday. The building stands because each floor holds, yet every floor is a potential hiding place for a ghost. Edgar Dijkstra warned against the temptation to pile up complexity without the steel of discipline. He called it the rallying cry of the sloppy thinker, and the warning still rings. Set the dangers to one side for a moment, and look at the grand result. This layered way of thinking has let humanity reach far. The climate model that runs on a supercomputer is written in languages whose ancestors did not exist when Maurice Wilkes sharpened his pencils in Cambridge. The avionics in an aircraft rely on real-time operating systems that enforce timing guarantees with the severity of a Swiss watch. A hospital infusion pump uses a tiny microcontroller that pretends to be a simple machine so that high reliability code can be proven correct. Your phone contains an operating system, a Java virtual machine, an interpreter for web pages, and a neural engine for machine learning, all stacked and interlocked like the floors of a Gothic cathedral. Billions of people walk around carrying these cathedrals in their pockets. The broader impact spills beyond convenience. Layers make it possible for teams separated by oceans to collaborate. A compiler writer in Zurich need not know the newest branch predictor design in a processor fab in Arizona. A data scientist in Nairobi can write in Python and stand upon libraries written in C that stand upon kernels written in C and assembly, which stand upon microcode and hardware. The arrangement accelerates progress, but it also obscures consequences. When software feels immaterial, the material world pays the bill quietly. Data centers turn electricity into heat with relentless appetite. Rare minerals are mined so that transistors can switch. E-waste piles up when old layers refuse to run on new ones. There is a persistent truth that binds the tower. Hardware and software are logically equivalent. Any operation described in software can be cast into gates if the need is great and the design sound. Any instruction in hardware can be simulated in software if you are willing to pay with time. Karen Panetta once put it this way: hardware is petrified software. That sentence is a key, and it opens a door where design becomes a moral choice. Speed at any price will tilt decisions toward hardware. Flexibility at any price will tilt them towards software. Most of the time, the right answer is a braided rope of both. Names linger in the halls like portraits. Alan Turing in Manchester, who gave us the abstract machine that still sits in the center of our theory. John von Neumann at the Institute for Advanced Study, whose architecture captured the essence of stored programs. Grace Hopper at Harvard, and later with the United States Navy, who insisted that machines should speak closer to human language and help the world take compilers seriously. John Backus and his team, who made Fortran work across a skeptical industry. John Koch, David Patterson, and John Hennessy, who showed that simplicity, executed with ferocity, could outrun Baroque grandeur. The IBM System/360 family that proved compatibility across models could be a business strategy, not only an engineering dream. The ARM lineage that made efficiency a first principle and conquered mobile computing. James Gosling and the Java virtual machine that resurrected the dream of portable code and made it industrial. Look closely at the way the levels meet, because that is where the drama lives. A compiler lowers an elegant loop into a handful of instructions that slice through data like a chef through herbs. The operating system steps in when the program asks for a file, translating a pleasant path name into block numbers on a device you will never see. The ISA decides how many registers the compiler can use before it must spill values to memory. The microarchitecture decides whether those memory accesses will be hidden by caches or amplified into stalls. The logic below decides whether a signal settles cleanly before the next clock tick. Each level is a promise to the level above. We will behave as if we are simple, so that you may be bold. The building has grown stranger with the rise of machine learning. There are new floors now, accelerators that speak in tensors and fused multiply-add systolic arrays that pass partial sums like whispers along pews. Compilers that schedule neural networks over silicon as if choreographing a ballet. Even here the old pattern holds. High-level frameworks describe a model. Middle layers rewrite and optimize. Low layers carry out kernels that look simple and repetitive, the kind of work an ALU loves. The tower learns, and when it does, it alters search engines, drug discovery, logistics, even art. The gap between human intention and machine action narrows, and something uncanny moves in. The mystery never ends, because the boundary between levels is not a wall, but a coast that erodes and accretes. Features that begin life as software libraries sometimes harden into silicon, the way wet clay becomes brick. Cryptography once belonged to mathematicians and programmers alone. Today, there are trusted enclaves on chips that perform secret arithmetic inside walls of metal. Video codecs hardened the same way, and then softened again as processors grew faster and the desire for flexibility returned. One person's hardware is another person's software, and if you listen at night, you can hear the hotel shifting its furniture, making room for new guests. There is a temptation to treat all of this as a parlor trick, a way to dazzle with layers and names. Resist that. The layers exist for a sober reason. They are how finite minds build infinite machines. Each level suppresses detail so that a person can think. Each level exposes just enough power so that a person can create. Strip away too many levels and you drown in switches. Add too many and you suffocate in bureaucracy. The art of structured computer organization is the art of choosing floors wisely, of knowing when to add one and when to tear one out. Stand once more in the humming room. The computer waits, uncomplaining, its face a field of quiet light. You type in a high-level idea, something like parse a file, render an image, learn the shape of a language. The request drops through the floors, transformed at each landing, from words to tokens to instructions to control signals, until at the bottom, electrons flow and transistors tilt reality by the tiniest of amounts. The result climbs back up the stairs, gathers its form, and appears before you as if nothing happened. That is the trick. The act feels like thought and looks like magic. Yet it is only patient engineering, always the same, always changing. The technology changed us in return. We learned to trust layers in our institutions because we live with layers in our machines. We created new trades, from systems programmer to compiler engineer to site reliability guardian. We formed companies around those trades, from IBM to Sun Microsystems to the startups that built browsers and engines and clouds. We rewired the economy around virtual machines running in places we cannot point to on a map. We altered the Earth by drawing power to warehouses of servers, then tried to mend the wound by making each level more efficient. We taught children to think in loops and conditions, to name things, to build towers of meaning one floor at a time. In the end, the old sentence remains the compass. Hardware and software are two masks for the same actor. Today's routine can be tomorrow's instruction. Today's instruction can be tomorrow's routine. The building stands because of that flexibility. The building endures because someone, somewhere, still knows how to climb down the stairs, open the basement door, and listen to the small instructions that run the world. Add 2 numbers. Check for 0. Copy from here to there. From those humble moves, through level upon level, we built a civilization that runs on code, and we gave it a heartbeat that sounds, in a quiet room, like the future clearing its throat.